Well, hello and welcome to today's webinar. I am Tom Sandry, and today we're going to explore the testing for earth resistivity and earth resistance. So, without further ado, let's get started.
Grounding and bonding systems ensure that electrical systems are safe from electric shock and fires by limiting the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines and a ground fault. Article 250 of the National Electric Code identifies grounding and bonding system installation methods. A properly installed grounding or bonding system for shielding, EMI, static, and lightning protection can help prevent cable failures, equipment damage, and power quality problems. These systems are also important for personal protection and compliance with OSHA. This webinar focuses on the various test methods for determining ground resistivity and measuring ground grids and connections used with electrical systems. The topics that we'll cover in this webinar today include soil resistivity, measuring soil resistivity using the 4-terminal test method, ground electrodes, ground resistance, the fall of potential or 3-terminal test method, effects of different probe locations, the slope method, a 3-terminal test method, triangular test method, a 3-terminal test, the direct method, a 2-terminal test, Stakeless method, or clamp-on test. We will also discuss step potential testing and touch potential testing. Soil resistivity measures how much the soil resists the flow of electricity. Measurements are represented by the Greek letter rho and are expressed in ohm meters or ohm centimeters, representing the resistance of a cubic meter of soil. Resistivity measurements have a threefold purpose. First, data is used to make subsurface geophysical surveys as an aid in identifying ore locations, depth to bedrock, and/or other geological phenomena. Second, resistivity directly impacts the degree of corrosion in underground pipelines. A decrease in resistivity relates to an increase in corrosion activity and therefore dictates the protective treatment to be used. Third, soil resistivity directly affects the design of a grounding system, and it is to that application that this webinar is directed. Soil resistivity is the key factor determining the resistance of a ground rod or grounding electrode and the depth at which it must be driven to obtain low ground resistance. Soil resistivity varies widely throughout the world and changes seasonally. It is determined largely by its content of electrolytes, which consists of moisture, minerals, and dissolved salts. Dry soil has high resistivity if it contains no soluble salts. In soil, conduction is largely electrolytic. Therefore, the amount of moisture and salt content radically affects its resistivity. Of course, the amount of water in the soil varies with the weather, time of year, nature of the subsoil, and depth of the permanent water table. The table shows typical effects of water on soil. Note that when dry, the two soil samples, topsoil and sandy loam, are good insulators with resistivity in excess of 10 to the 9th power ohm centimeters. With a moisture content of 15%, however, note the dramatic decrease in resistivity. Pure water has an infinitely high resistivity. It is the naturally occurring salts in the earth that dissolve in water, lowering the resistivity. Not much information has been collected on the effects of temperature on soil resistivity. Two facts lead to the logical conclusion that an increased temperature will decrease resistivity. First, water present in soil mostly determines resistivity. And second, an increase in temperature notably decreases the resistivity of water. The results shown in this table confirm this. Note that when water in the soil freezes, the resistivity jumps appreciably. Because soil resistivity directly relates to moisture content and temperature, it is reasonable to assume that the resistance of any grounding system will vary through the different seasons of the year. Since both temperature and moisture content become more stable at greater distances below the surface of the earth, it follows that for a grounding system to be most effective all the time, it should be constructed with the ground rod or rods driven down a considerable distance below the surface of the earth. Best results are obtained if the ground rod reaches the water table. Soil resistivity measurements are commonly made with a four-terminal test method. As the name implies, the four-terminal method requires the insertion of four equally spaced and inline test rods or electrodes into the area under test. A known test current is passed between the outer electrodes. The potential drop, a function of resistance, is then measured across the two inner electrodes. Dr. Frank Wenner of the U.S. Bureau of Standards, now known as the National Institute of Standards and Technology, or NIST, developed the theory behind this test in 1915. Wenner showed that if the depth of the test electrodes was kept small compared to the distance between the electrodes, the following formula would apply. Rho equals 2 pi AR, where rho is the average soil resistivity to a depth equivalent to the electrode spacing in ohm centimeters. Pi is the constant 3.14159. A refers to the distance between the test electrodes in centimeters, and R is the resistance value measured by the test set. The recommended depth of the test electrodes is 1/20th the distance between them. For example, if the distance between the test electrodes is 450 centimeters, the depth of the test electrodes should be no more than 22.5 centimeters. Before we look at a sample test, let's examine soil composition. Soils of ashes, shale, or loam tend to have the lowest soil resistivity. Soils of gravel, sand, or stone have the highest soil resistivity. As mentioned before, moisture content, temperature, and salt will affect soil resistivity. Soil that contains 10% moisture by weight will be as much as 5 times lower in resistivity than that which contains 2.5%. Soil at room temperature will be as much as 4 times lower in resistivity than at 32 degrees. So, the time of year you conduct the test can play a major role in the results. Finally, salt content factors in the results in a very big way. Changing the composition by 1% can reduce soil resistivity by as much as a factor of 20. Therefore, a quick visual analysis of the job site can give you a good idea as to whether you can expect low resistance from the installed grounding electrodes made up of a single ground rod, or if you will need to install several rods to achieve the required results. These conditions should be written down and kept with the test results. Temperature, moisture, and soil type are easily identified. Salt content might be more difficult to determine. Let's work through a sample soil resistivity survey. Since most commercially available ground rods tend to be 8 to 10 feet long, we will conduct our sample survey based on an expected soil resistivity at a depth of 10 feet. Using the Winner 4-terminal test method, we will space our 4 test electrodes an equal distance apart in a straight line with spacing equal to the depth to be tested. Since in our example we are testing to a 10-foot depth, our test electrodes will need to be spaced in a straight line 10 feet apart. To get a good indication of soil resistivity in the test area, we will take 5 measurements and average them for our final answer. 4 of the measurements will be taken in a square pattern, and the final measurement will be on the inside diagonal of the square. To use the simplified soil resistivity formula of rho equals 2 pi A, the depth of our electrodes should be no more than 1/20th the spacing of the electrodes. Therefore, since the spacing is to be 10 feet, 1/20th would be a depth of 0.5 feet or 6 inches. Once our test electrodes are placed at the appropriate spacing and depth, we can connect the 4-terminal test set and take our measurements. Observe and write down your test results. For our practice sample, let's assume that the average of the 5 measurements was 3.4 ohms. Now we're ready to apply the formula. First, we will convert 10 feet to centimeters by multiplying 10 times 30.5, which gives us 305 centimeters. The average soil resistivity to a depth of 10 feet would equal 2 times 3.14159 times 305 centimeters times 3.4 ohms, equaling a resistivity of 6,516 ohm centimeters based on a 10-foot depth. Let's calculate the depth needed for a new ground rod installation. For this, we will use a calculating tool called a nomograph. To begin with, we need to make a few decisions. First, what is the desired grounding electrode resistance needed? Second, what is the diameter of the ground rods we will use? We can use the nomograph to calculate the depth required to achieve our objectives with these 2 answers, plus the measured soil resistivity. Let's say we need the resistance for the grounding system to be no more than 10 ohms, and we choose ground rods that are 5/8 inch in diameter. Looking at our nomograph, we have 5 scales to work with. The R scale represents the desired resistance needed for our work, in this case 10 ohms. The P scale represents soil resistivity. Our average value is 6,516 ohm centimeters, obtained using a 4-terminal test set employed using the Winner test method. The D scale represents the depth and is what we will use to find our answer. The K scale contains constants that will assist us in finding the depth. Lastly, the DIA represents the ground rod's diameter. Our first step will be to mark the desired ground resistance of 10 ohms on the R scale. Next, we will mark our measured ground resistivity of 6,516 ohm centimeters on the P scale. Using a straight edge, we can draw a line from the R scale through the P scale and extend it until it intersects the K scale. Using the DIA scale, we will mark our electrode diameter of 5/8 inches. Once again, we will use our straight edge to draw a line from the DIA scale through the K scale and intersect the D scale. The intersection on the D scale will be the depth required by a single 5/8 inch electrode to achieve a 10 ohm ground resistance. In our example, we will require a 32-foot depth. We may want to use multiple ground rods rather than a single rod driven to a 32-foot depth. There are a few important points to consider when driving multiple rods. The first is that driving additional rods will not achieve a linear result. For example, 3 10-foot rods will not yield the same results as a 30-foot rod. We need to apply an adjusting factor. Secondly, to achieve the best effect of additional rods, they should be spaced apart at equal to the depth and preferably at twice the depth. For example, multiple 10-foot rods should be spaced 20 feet apart to avoid being in the sphere of influence of each other. The adjustment factor required for multiple rods is shown in the following table. If we use 3 10-foot rods in parallel instead of one 30-foot rod, we would expect each rod to contribute 1.29 times the theoretical value. Stated another way, if we divide the 10 ohms needed by 3 to find the expected value of each rod, we get 3.33 ohms. Applying the adjustment factor from the table for 3 rods in parallel, we get 3.3 times 1.29, or 4.3 ohms contributed by each rod for 12.75 ohms. We would need to drive a 4th rod to get below our desired 10 ohms. Now let's discuss ground. Ground is a conducting connection by which a circuit or equipment is connected to the earth. The connection establishes and maintains as closely as possible the earth's potential on the circuit or the equipment connected to it. A ground consists of a grounding conductor, a bonding connector, its grounding electrode or electrodes, and the soil in contact with the electrode. The purpose of the ground, besides protection of people and equipment, is to provide a safe path for the dissipation of fault currents, lightning strikes, static discharges, EMI and RFI signals, and interference. The resistance of an electrode has the following components: the resistance of the metal or material and that of the connection to it, the contact resistance of the surrounding earth to the electrode, and finally, the resistance of the surrounding earth to current flow or earth resistivity is often the most significant factor. Grounding electrodes are usually made of conductive metal, copper or copper clad, with adequate cross sections, so the materials and connections' overall resistance is negligible. Further, the National Institute of Standards and Technology has determined that the resistance between the electrode and the surrounding earth is also negligible if the electrode is free of paint, grease, or other coatings, and if the earth is firmly packed. Therefore, the only component remaining is the resistance of the surrounding earth. The electrode can be considered surrounded by concentric shells of earth or soil, all the same thickness. The closer the shell is to the electrode, the smaller its surface, hence the greater its resistance. The further away the shell is from the electrode, the greater the surface area, hence the lower the resistance. Eventually, adding shells at a distance from the grounding electrode will no longer notably affect the overall earth resistance surrounding the electrode. The distance at which this effect occurs is referred to as the effective resistance area and is directly dependent on the depth of the grounding electrode. In theory, the ground resistance may be derived from the general formula: resistance equals resistivity times length divided by area. This formula illustrates why the shells of concentric earth decrease in resistance the further they are from the ground electrode. Resistance equals the resistivity of the soil times the thickness of the shell divided by the area. In the case of ground resistance, uniform soil resistivity throughout the volume is assumed. However, this is seldom the case in the real world. The equations for electrode systems are complex and often expressed only as approximations. The most used formula for a single ground electrode system, developed by H.R. Dwight of the Massachusetts Institute of Technology, is as follows. R equals the resistance in ohms of the ground rod to the soil. L equals the grounding electrode length. Lowercase r equals grounding electrode radius. And rho equals grounding resistivity in ohms centimeters. The National Electric Code, NEC, states that the resistance to ground shall not exceed 25 ohms. This is an upper limit and guideline, since much lower resistance is often required. How low should a ground be? An arbitrary answer in ohms is difficult. The lower the ground resistance, the safer, and for positive protection of personnel and equipment, it is worth the effort to aim for less than 1 ohm. It is generally impractical to reach such a low resistance along a distribution system, transmission line, or small substation. In some regions, resistances of 5 ohms or less may be obtained without much trouble. In other regions, it may be difficult to bring the resistance of driven ground rods below 100 ohms. Accepted industry standards stipulate that transmission substations should be designed not to exceed 1 ohm. The maximum recommended resistance in distribution substations is 5 ohms or even 1 ohm. In most cases, the buried grid system of any substation will provide the desired resistance. 5 ohms is the accepted value in light industrial or telecommunication central offices. For lightning protection, the resistors should be coupled with a maximum resistance of 1 ohm. These parameters can usually be met with the proper application of basic grounding theory. However, circumstances will always make it difficult to obtain the ground resistance required by the National Electrical Code or other safety standards. Several methods of lowering the ground resistance can be employed when these situations develop. These include parallel rod systems, deep driven rod systems utilizing sectional rods, and chemical treatment of the soil. Additional methods may include buried grids or plates, buried conductors counterpoise, electrically connected building steel, and electrically connected concrete reinforced steel. Electrically connecting to existing water or gas distribution systems was often considered to yield low ground resistance. However, recent design changes utilizing non-metallic pipes and insulating joints have made this method of obtaining a low resistance ground very questionable and in many instances unreliable. Now, let's look at techniques for measuring the ground resistance of a grounding system. Consider the diagram shown to understand the principles of earth resistance testing. Bear in mind our previous observation regarding the earth shell diagram. With increased distance from an electrode, the earth shells have greater surface area and lower resistance. Now, assume that we have 3 rods driven into the ground some distance apart and a current applied as shown in our diagram. An ammeter measures the current between rods 1 and 2. A voltmeter measures the potential difference or voltage drop between rods 1 and 3. If rod 3 is located at various points between rods 1 and 2, preferably in a straight line, you can get a series of voltage readings. By applying Ohm's law, or resistance equals voltage divided by current, you can determine the Earth's resistance at any point measured. For example, if the measured voltage V between rods 1 and 3 is equal to 30 volts, and the measured current I is 2 amps, the Earth's resistance R at that point will be 15 ohms. This is the basic construction and theory behind modern ground resistance test sets used during field testing. A series of resistance values can be plotted against distance to obtain a curve. Note that as rod 3 is moved away from rod 1, the resistance value increases, but the increase gets less and less until the point is reached where the rate of increase becomes so small that it can almost be considered constant. 20 ohms for the example shown. The earth shell between rods 1 and 3 have such a great surface area that they add little to the total resistance. Beyond this point, as rod 3 approaches the earth shell of rod 2, resistance gradually picks up. Near rod 2, the values rise sharply. Now, let's say that rod 1 is our electrode under test. From a typical earth resistance curve, such as the one shown, what is the resistance of the earth rod? We can call rod 2 our current reference probe and rod 3 our potential reference probe. The correct resistance is usually obtained if a potential reference is placed at a distance from the center of the earth electrode under test at about 62% of the distance between the earth electrode under test and the current reference probe. For example, the distance from the earth electrode to the current reference probe is 100 feet. Taking 62% of this distance, we get 62 feet. The resistance for this distance is 20 ohms. This is the measured resistance of the electrode under test. Note that at least 8 to 10 readings should be taken at equally spaced intervals to obtain an ideal earth resistance curve. True resistance will be obtained when the curve flattens out, typically 62% of the distance. Taking readings over greater distances or in different directions from the electrode under test will help confirm the test results. Now you may ask, if the correct location for the potential reference probe P is always 62% of the distance between the earth electrode under test and the current reference probe C, why bother with tests at other locations for potential probe P? Why not just drive the potential probe in at the 62% point and assume that the measured resistance is the correct earth resistance? Well, the following should help answer this question. Consider the illustration shown, which shows earth shells around the electrode under test and reference probe C. Probe C is so close to the electrode under test that the earth shells seriously overlap. Now, you don't get the leveling off of the measured resistance as the potential probe P is moved away from the electrode under test. The shells of the current reference probe C add to the shells of the electrode under test, so that the resistance keeps increasing. We've been discussing the testing of a single ground rod up until this point. How should we establish the placement of the current inject C probe when dealing with a multiple electrode system? When measuring ground grids, we would use the longest diagonal distance to determine the placement of the C electrode. In our example, we show a 30-foot diagonal. Based on our table, we should place the C probe 260 feet from the ground grid. Suppose you are facing one or both of these everyday situations. 1. An enormous ground grid. Or 2. Little or no room to drive reference probes. A large grid, such as those that underlie a substation or encircle a transmission tower, will have a large electrical field in the soil. Getting the current injection probe placed beyond this influence typically takes several hundred feet and can be prohibitive. The environment may not afford reasonable spacing. For example, the site could be in a downtown area surrounded by roadways or other boundaries. As the problem of limited space and other daunting situations often arise, methods have been derived to complete the test and go ahead with business as usual. One such method that allows this is known as the slope method. To perform the slope method, the earth resistance is measured at separate placements of the potential reference probe, and the resistance curve is plotted from the results. Key locations for the potential reference probe are at 20%, 40%, and 60% of the distance between the current reference probe and the grounding system under test. Additional test points are used to validate the pattern of the resistance curve. Validating the curve will show any incorrect points that can be rechecked or ignored. Once the curve is drawn, we need to calculate the slope coefficient, mu. To do this, we take the resistance value recorded at our key potential reference probe locations, and we call them R1, R2, and R3 respectively. To calculate the slope coefficient, we use the formula R sub 3 minus R sub 2 divided by R sub 2 minus R sub 1. This will provide us a measure of the change of slope of the ground resistive curve. A relationship can be derived between the slope coefficient, the distance to the current probe, d sub c, and the distance at which the potential probe would measure true Earth resistance, or P sub t. The table shown gives values of P sub t divided by c for various values of slope coefficient, or mu. From this, a simple equation yields the distance the potential probe should be placed using the known distance to the current reference probe. Let's work through an example. Suppose that the key measurement points at 20, 40, and 60% of the distance to the C probe were 2.1 ohms, 4.8 ohms, and 6.6 ohms, and the distance to the C reference probe is 100 feet. To calculate the slope coefficient, we would take 6.6 minus 4.8 divided by 4.8 minus 2.1, which would give us a slope coefficient, or mu, of 0.67. Looking at the mu value of 0.67 on our reference table, the P sub t divided by the C value comes out to be 0.602. To find the true location for the P reference probe, we would simply take 0.602 and multiply it by the known distance of the C reference probe, or 100 feet in our example. This would give the true P reference probe position pinpoint at 60.2 feet. Here is an example of a software application that performs the slope method calculation based on our measured data. This software shown is called PowerDB Lite. Another three-terminal test method worth mentioning is the triangular test method. This method requires two auxiliary electrodes. It is used when the full follow potential method is impractical because electrode alignment is not possible, or obstacles prevent enough distance for the P, or potential, and C injection electrode placement. To perform the triangular test method, set up the P and C electrodes so that they form an equilateral triangle, all sides equal in length, with the earth electrode E to be tested. Example, E to C would equal 100 feet, E to P would also equal 100 feet, and P to C would equal 100 feet. Conduct a 3-pole follow potential measurement and record or write down the reading. Next, move the P electrode to the opposite side, again forming an equilateral triangle, repeating the measurement process, recording or writing down the results. Compare the two measurements. If the two values measured differ significantly, the P electrode is in the sphere of influence of E, C, or both. You must then increase the distance for P and C and repeat the measurements. If the values obtained are within a few percent of one another, the measurement can be considered valid. The results of this method may still be uncertain. However, because even when the values measured are similar, the sphere of influence may still overlap. To confirm they are not, increase the distance for C and P and repeat the two measurements. The direct or two-point measurement method is an alternative method when an excellent ground is already available. Finding room to drive the two auxiliary rods in congested areas may be a problem. The two-point measurement method may be applied. The reading obtained will be that of the two grounds in series. Therefore, the water pipe or other ground must be very low in resistance to be negligible in the final measurement. The lead resistance will also be measured and should be deducted from the final measurement. This method is not as accurate as a three-point method or a fall of potential method discussed earlier, as it is particularly affected by the distance between the test electrode and the dead ground or the water pipe. This method should not be used as a standard procedure, but as a backup when working in tight areas. Stakeless testing is one of many methods of measuring earth electrode resistance. However, what sets this method apart is that it is the only method that does not require the use of auxiliary test electrodes or test leads. Let's look at the following grounding system to understand how the stakeless method works. Each element in the circuit, the water pipe, system earth, and other electrodes, has a resistance to earth. The clamp-on earth tester treats these elements as being parallel and in series with the electrode being tested. Therefore, the instrument will measure the whole loop resistance and not just the electrode under test. If we were to add the parallel resistances together to obtain an equivalent resistance, we would obtain a value of 2.9926 in this example. This equivalent resistance would add to the resistance of the electrode under test, giving us a final reading of 12.99 ohms. Let's look at how the instrument works to understand this measurement technique better. Inside the clamp head, there are two clamps. One core induces a test current, and the other measures how much was induced. The input or primary voltage of the test current inducing core is kept constant, so the current induced into the test circuit is directly proportional to the loop resistance. The important thing to remember is that clamp-on earth testers effectively make loop resistance measurements. Therefore, stakeless measurements are loop measurements. That leads us to the key rules when using a stakeless tester. Our first rule is that there must be a loop resistance to measure, a series parallel resistance path, and the lower the better. Look at the two circuits shown. Note that more parallel paths lower the total resistance value. Hence, the more parallel paths, the lower the effect on the reading for the electrode of interest. Now, our second rule. The earth path must be in the measurement circuit in order to measure earth resistance. This sounds obvious, but if you have metal structures involved, there may be a current path through the connection rather than through the earth mass, as seen here. Of course, you may want to place the clamp here to verify a connection, and that's fine. But be sure you are aware of what you are testing and that what you think you are testing is what you are actually testing. Now let's talk a little bit about touch and step potential testing. Hazardous conditions may develop that place the worker's body in series or parallel with circuits that can produce a current through the body. Step potential. This is the difference in surface potential experienced by a person bridging a distance of 1 meter with the feet without contacting any other grounded object. touch potential. This is the difference in potential between a grounded structure or station and the surface potential at the point where a person is standing, while at the same time having a hand in contact with the grounded structure or object. To perform the step potential test, first connect the E test lead to the grounding system. Next, insert the injector electrode at the appropriate distance away from the grounding system where the anticipated fault will occur and connect the H lead to it. Third, insert 2 electrodes 3 feet apart, the distance of a human step, at the approximate location of the expected position of the person and attach the E sub S and S leads to them. All electrodes should be in a straight line. Start the test using the 4-point ground test mode and record the resistance reading. Estimate the expected fault current and multiply it by the measured resistance reading to determine the step potential voltage. V equals I times R. So let's use an example of 1000 amps. If our fault current is 1000 amps and our resistance we measured is 0.4 ohms, the step potential would be 400 volts. Now let's look at performing the touch potential test. First, connect the E and E sub S leads to the metal object that would be touched. Insert an electrode approximately 1 meter, 3 feet, from the object and connect the S lead to it. Insert an electrode at the approximate location of the expected fault and connect the H lead to it. Start the test using the 4-point ground test mode and record the resistance reading. Estimate the expected fault current and multiply it by the measured resistance to determine the touch potential voltage. V equals I times R. So, in our example, we will assume 1000 amps of fault current. A measured resistance reading of 0.2 ohms. That would then give us a touch potential of 200 volts.
And that concludes our webinar today on earth resistivity and earth resistance. Hey, if you like this content, please don't forget to subscribe, hit that bell for notifications, and give us a thumbs up in the like. Until next month, I'm Tom Sandry. Be safe out there.